G'day and welcome to this second video, the second of three, in which I'm explaining how to integrate. In the previous video I talked about the 6 basic functions: powers of x, sine, cos, tan, the 3 trig functions, exponentials and logarithms, and how we integrate their pure forms, and tried to address the confusion that some students have over some of the shortcuts. In this video I'm going to look at what happens when we have a chain, that is a function inside the function. So I've already drawn them up, where we have a function inside the power, a function inside the sine, inside the cosine, and so forth. Let's review first of all how we find the derivative. The outside function here is the power, and the way we would deal with that is we would the n would come down and we'd have whatever is inside to the power n minus 1. But then we would multiply, using the chain rule, we would multiply by the derivative of what's inside. And I'm actually going to write it at the front here, rather than at the back. They're multiplied, so the order doesn't matter. I'm going to write it in the order I prefer. In the case of sine, the derivative, I know this is going to be a bit cramped fitting all 6 on the board, but I want you to see these. The derivative of sine is cosine of whatever is inside. And again, using the chain, we multiply by the derivative of the function inside, which I'm going to write out the front. Here, the derivative of cosine is negative sine of whatever's inside. Again, following the chain rule, we multiply by the derivative of the function inside. Here we do take the derivative of the tangent, so dy dx. The derivative of the tangent is sec squared, whatever is inside. My goodness, I am cramping them in. And to finish the chain, we multiply by the derivative of what's inside. I hope you're seeing a pattern already. I hope, if you've been struggling, I hope this is new to you. I hope this all makes sense. If we find the derivative here, and I'll just move down a bit to avoid the congestion. The derivative of an exponential is itself, but because we have a function inside, we multiply by the derivative of that function. That's our chain rule. And finally, the derivative of a logarithm is 1 over whatever is inside times the derivative of the function inside. What do you notice? Well, there's a lot of black marking on the board, but I want you to see a structure. First of all, every single one of them, without exception, every single one, because of the way the chain rule works, has the derivative of the function at the front. Every single one of them. Also, what's left is our standard derivative. The derivative of a logarithm is 1 over something. The derivative of the exponential is the exponential. The derivative of tangent is sec squared. The derivative of cos is negative sine. The derivative of sine is cos. And the derivative of a power of n, power of x to the power n, is n times x to the n minus 1. So we have the standard forms that we saw in the last video, the same 6 standard forms, with a function inside and the derivative of the function outside. That's the pattern we look for. And that's what I want to drive home. People try, because there's a constant here, because there's a negative here, and sometimes because the derivatives themselves turn out to be whole numbers, people try to invent all shortcuts to move the number outside and rearrange. And my experience is that for a lot of students it creates confusion. So if you're confused, I want to suggest that you just follow this pattern. Let's do a few integrals. I'll try and do one of each and we'll see what we get. So let's imagine we needing to solve or find this integral. X squared minus 5x to the power 8 dx. I think I've got the wrong pen here. This might make life a bit easier. And the derivative of this, well, let's start by discussing this. If I had to integrate this, where I have a function inside a power, I know I'm using the power rule. And to integrate, I need this pattern. I need to have the derivative out the front. If it's not there, I cannot integrate it, not easily. I'd have to use some other method. Perhaps expand all this, which would be a bit of a nightmare with power of 8. You'd end up with a lot of terms. But if you happen to have the derivative of this out the front, this is the pattern. There's our derivative, here's our power. Now we've got two alternatives at this point. If I use the shortcut, I'd simply say that following this pattern, it's going to be x squared minus 5x to the power 9 over 9 plus c. You'd have to see my last video to see why that would be true. But if you would prefer, as I recommend actually at this point, because we're starting to get to more complicated territory, if you would prefer to follow this pattern exactly, notice there's an n at the front as well. Now if this is 1 less than that, so if this is an 8, this has to be a 9, and I would love to have a 9 there, in which case, to compensate, I would write 1/9 out the front, because 1/9 of 9 is 1, it makes no difference. And now this integral is exactly that pattern. I've got the n, I've got the derivative, I've got the function to the power, and the power and this number match. So I can integrate, and what I would get would be 1/9, and the integral of all of this will be that function to the power one more, x squared minus 5x to the power 9. And I hope you can see that those are the same. 1/9 of that is the same as that divided by 9. It's a personal preference. It's one of the few personal preferences I really don't mind what you do. I suppose I don't mind at all, but I'm going to make some recommendations with the others. But a lot of students who like to avoid the confusion will learn to write these 6 structures and learn to match the integral always to one of these 6 structures. So I have some students who do the shortcut, but I have a lot who prefer to get this pattern exactly right. And it's quite comforting and settling to do it. So let's look next at the trig functions. Actually, it was rather silly of me. I realised I didn't share one little thing with you. Let's imagine we have an integral of x squared minus 4x to the 11, for example. And we've got x minus 2 out the front. Now, it looks like we've got the right structure, but is this the derivative of the function? We've got a function to a power, so we've got this structure. We need the derivative of this function at the front. What's the derivative of x squared minus 4x? It's 2x minus 4. That's not what we have, but we can make the adjustment just with a coefficient, with a whole number, because that's equal to 2 lots of x minus 2. So if I place the 2 here, I'm going to have to move this integral sign. If I place the 2 there, and a half, they compensate, and that now is the derivative of that. So I've got the derivative, I've got the function to the power, and if I'm doing it the longer way, or if you like the more patterned way, I'd also want the correct number at the front. So I would multiply by 1 more than that. which means I also need to compensate for that out the front. Because what I'm trying to do inside the integral is to match that pattern exactly. So I've got the function to power, the number out the front is 1 more than the power, so I've got that now, and this f dash x is the derivative of the function, and 2 lots of x minus 2 is the derivative of that. That's exactly what I want. Now outside, 1/12 of a half is 1/24th. And now because that follows the pattern exactly, the integral will be that, which is the function x squared minus 4x to the power 12. Which of course is probably more properly written as that. But if you can have these patterns written in front of you and memorise them, they'll stand you in good stead. Now we'll look at the trig functions. I'll use blue this time. Let's imagine we're integrating. We're going to integrate a cosine. Let's say we're integrating a cosine of e to the 2x dx. Now if you have to integrate that by itself, you've got significant problems. It involves another method. To use this technique, the chain method, we needed to follow this pattern, and we would like to have the derivative of this function out the front. What's the derivative of e to the 2x? Well, using the chain rule, it's e to the 2x, the same function, multiplied by 2. So if that was out the front, that would be perfect. This is the derivative of that. So we've got the derivative of the function out the front, and we just match the pattern beautifully. And the integral would be sine of whatever the function was. Now if the 2 happened not to be there, we would have to create it. Let's imagine it had a 5. What we would do is we would move the 5 out the front. We would then multiply inside by 2 and outside by a half, so that we have the exact pattern we want. And all it would mean is that this would now be multiplied by 5 on 2. So once the basic structure is there, all that you muck around with, all that you rearrange, are just the numbers at the front to get them right. So there's that integral. Let's change to black and we'll deal with this. What if we're integrating sine of, just log x. There we go, dx. What if that is our integral? Well again, if I'm integrating sine, I look along here, there it is, there's my sine to integrate, and to integrate it I really want that pattern. Now, what is the derivative of the function inside? What's the derivative of log x? It's 1 over x. That's what I would love to see out the front. 1 over x, or sometimes it would be written all over x, but I'll put the 1 on x out the front. And that would be our pure pattern. Now, if, for example, we've been given this, it's handy being able to do this on a whiteboard. Let's imagine we had that integral to perform, to calculate. What I would recommend doing is move the 6 outside. Sorry, things bumping here. Oh, that's awful. Logarithm. And if you prefer that over x, you can write as 1 over x out the front. In other words, you write it, as long as it's mathematically correct, you rearrange it to fit the structure you want. So we've moved the 6 out the front, we've moved the 1 over x out the front, written as sine log x dx. That is the same as that. Does this conform to the pattern? Well, we're integrating the sine. We've got sine of a function, and yes, the derivative is at the front. Oh, but we want a negative sign. Let's do that in blue. If I want a negative in here, I must multiply by a negative from the outside. A negative 6 times a negative gives me plus 6. That compensates, and this pattern now is exactly what I need. So my answer is going to be negative 6 times the integral of this package, which is that cosine of whatever the function was inside. That's it. But we've got it, we've bashed it into shape, if you like, put it into the form we want. Let's move to tan. Let's try this integral. The integral of sec squared cos x dx. Now again, this would be a higher order, a much more difficult integral if we were missing the derivative out the front. But if you're doing a standard course in high school, you will have the derivative there and you should look for it. What's the derivative of cos x? Well, the derivative of cos is negative sine x. So let's imagine we've got a sine x here. And let's imagine we've got a number, 2/3. Let's imagine we've got that. That would look absolutely horrendous to integrate, but I want you to look carefully at the structure. By looking at it, the most complicated part is here, and you see you've got sec squared of a function. You think, sec squared, that's familiar. Sec squared of a function. That might be useful. Is the derivative out the front? Well, basically, yes it is. We're in business. Let's, first of all, get rid of the 2 and the 3. They're cluttering things up. And we'll leave the sine x at the front. And the sec squared x, or the sec squared of cos x dx. Now, check again. Does it follow our pattern? Here's our sec squared of a function. We've got that. Is the derivative out the front? Well, the derivative of cos x, oh, it's negative sine, the derivative. We need a minus sign. So I'll put a negative sign there and a negative there, because remembering they're multiplied, 2 negatives make a positive. So they compensate for each other. Now is it right? Sec squared of a function, the derivative of cos is negative sine. That is perfect. That is exactly that pattern. So if I integrate it, I'm going to get exactly that pattern. So the negative 2/3 stays at the front, because it's not part of the integral, times, and this integral is exactly tan of whatever the function is inside, which in this case was cos x. And if you wanted to write that as a complete fraction, you'd write negative 2 tan cos x over 3. It's a matter of personal preference whether you would rather have the fraction out the front or as part of the whole expression, the whole term. But there it is. That's that one. 2 to go, and I do encourage you to stay and watch, because there's some fascinating stuff to share about the logarithms, something to watch out for. But let's wipe this and see what we do with exponentials. Well, let's do something creative. We're going to integrate the exponential, or the e to the power, let's just make it sine x dx. It's a nice simple one. Let's put a number in front, 7. Let's make it even worse. Let's say we have this ugly looking thing. Oh, let's even make it worse still. There we go. So we've got this job to do. There are numbers everywhere, but we look for the essential structure. The essential structure is it is an exponential to a power. And that should get you thinking, and you think, exponential to a power, I could use this pattern. Now, is the derivative out the front? Now, in this case, it's not, which would make this very difficult to do. But let's imagine we're just going to put it in here. What is the derivative of sine x? Well, it's cos x. Don't worry about the constants for the moment. Now we have a structure we can use. We have the exponential to a function, and we have the derivative of the function, in essence, out the front. Let's put it into that exact form. First thing we do is get rid of the 7 and the 5 out the front, because they're just cluttering it up at the moment. Write our cosine of x, our exponential to the 3 sine x, e to the 3 sine x dx. There's our pattern, exponential function. What is the derivative of 3 sine x? It's actually 3 cos x, isn't it? So we actually need 3 cos x here to follow this pattern exactly. If I put a 3 there, I need to have a third out the front, or another way of doing is just multiply the denominator by 3. So there we have it. The derivative of this function is exactly that. So now, putting it together, I've got 7 over 15, and this pattern followed exactly means that when I integrate I get exactly that, which is e to whatever the function was. And again I can tidy that up and write 7e to the 3 sine x on 15 plus c. So there you have it. What looks like a very, very complicated piece of work, provided you take the time, and it just takes one step to do it, provided you take the time to get that structure right, the actual integral itself is simple because you're following that exact pattern in reverse. And that's what I want you to practice. That's what I recommend you practice. And if you follow that, you should be able to do these integrals in certainly less than a minute, and quite possibly for a lot of them in under 30 seconds. Not quite as fast as you differentiate, but certainly a lot faster than you might have previously imagined. So, normally I do this when you're not watching. I'm going to clean this off and we're going to deal with a logarithm. Okay, let's look at a logarithm. What's the integral of 1 over tan x dx? Now I can put a number there. Let's do that. In that form, could be very difficult to do, and we'll talk about that in a moment. It's actually easier than you think, this particular one. But if I see a fraction with a function on the bottom, the chances are very high. It's not certain, because there are exceptions. We had one of them earlier, when we had a function with a logarithm in the middle inside, and its derivative was 1 over x, so that put an x on the bottom. So there are occasions when you'll get x or some function of x on the bottom when it's not this, but often it will be, where we have a function on the bottom and we need this derivative on the top. I could write this f dash x over fx. So it's the only one of the 6 that we have a pure, obvious fraction. What's the derivative of tan x? Well, we know the derivative is sec squared x. If there's no sec squared on the top, it doesn't follow the pattern. We've got to do something else. But let's imagine we have it. That follows that pattern beautifully, doesn't it? Function, derivative. Function and its derivative. So all I would do here is I'd move the 4 out the front. And now, because that follows that pattern beautifully, when I integrate, I'm going to get exactly that. The logarithm of whatever the function was on the bottom. So I'm going to get the logarithm of tan x. And there it is. The integral done. Now, since I mentioned this one, I might actually do it. I was going to integrate tan x, but let's do 1 over tan. So we'll rub this off. I want you to see that there is a little bit of a trick with tangents, and I strongly recommend that you explore this. You know, I hope, that tan x is sin x on cos x. I hope you realise that. That means, doesn't it, that 1 over tan x, or cot x if you like, cotangent, is cos x on sin x. Is that true? Well, if that's the case, I can write this integral as the integral, instead of 1 on tan x, as cos x on sin x. We have a fraction. We have a function on the top and the bottom, and out of all the patterns, this is the one it could potentially be. On the bottom, we have a function sin x, and on the top, what's the derivative of sin x? Well, the derivative of sin x happens to be cos x. This is perfectly adapted to that. And consequently, I don't have to make any changes because I have the function and its derivative. Therefore, when I integrate, I'm going to get the logarithm of the function. So the answer is logarithm of sin x. Let's see. How nice is that? What looked to be rather horrible turned out, because we had an identity, a trigonometric identity we could use, we converted to this, and it turned out to be a logarithm of sine. Well, we've covered a lot of territory. I think it's probably been, some of these videos are going a bit too long, I think. But I like to be thorough, and I hope that by the time you watch one of my videos once, you will and truly understand the process. Rehearsing very quickly, learn to write these 6 derivatives, learn to recognise these 6 patterns, and when you see integrals that are close to that pattern, learn to mould the integral so it fits the pattern exactly, so you can make the derivative take place, make the integral take place with considerable ease. And I hope that has helped you a great deal. Now, this is all based on the chain rule. The next video is going to look on a process that comes from the product rule when we differentiate, and when we reverse that we get what is called integration by parts. So we'll deal with that in the next integral, and it's a rather more advanced technique. In our Australian schools, our advanced students do this, but what we call our extension students use use integration by parts. So that's the next video coming, if you're interested in seeing it. In the meantime, if you're not a subscriber, I encourage you to subscribe to be informed of these next videos. Please leave a comment and like the video, and as always, I thank you for watching.